What we are doing today is solving logarithmic equations. And I mentioned at the beginning of the class, we turned the equations yesterday, which were exponential, into logarithmic equations, but they weren't really logarithmic equations. What makes an equation logarithmic is x is part of the argument of a logarithm. Not a coefficient of a logarithm like yesterday's stuff, but part of an argument. We're going to have to remind ourselves about what extraneous roots are. An extraneous root, just in a very general sense, is a solution that you get to an equation doing everything right, but it's just not a valid solution. Okay? We encounter these when you solve radical equations because maybe you get, there's a number of reasons, but maybe you get a solution for x that when you put it into the original equation, you end up having to take the square root of a negative. Can't do that. Okay? Maybe when you solve a trigonometric equation that has tangent in it, you do all this work and you use identities, and at the end you get theta equals pi over 2. But tangent of pi over 2 is not defined. So by changing the equation, you, I guess, open the door for values for the solutions that may not be solutions to the original equation because you've changed the equation. And the reason why we're going to get extraneous roots here, I want to get this out of the way right now. The reason why you'll get extraneous roots here is because whenever you take a logarithm of an argument, I'm just using capital A for the argument must be greater than 0. You cannot take a logarithm of 0 and you cannot take a logarithm of a negative. Because, you know, just to go through this again, and we have time, if I say to you, what is log base 2 of 0, I'm asking you to find an exponent that you raise 2 to get 0. Well, 2 raised to any exponent will always be a non-zero number. It will always be a positive number. If I said to you, what is log base 2 of negative 8? The same thing holds true. You cannot raise 2 to an exponent and get a negative result. So this is absolutely key to what we're doing today. That the argument in any logarithm must be greater than 0. All right, let's get started. You're going to discover there are a number of different types of equations that we're going to be solving, and they fall into a certain, this first one falls into a particular category, and so does the second one. Look at this very carefully. Log base 6 of 2x minus 1 equals log base 6 of 11. If that's true, what else must be true? I know that's a vague question. I understand that. But is there a different equation we can come up with because of that statement? Ariana?
Is there parameters on x?
Pardon me?
Is there parameters on x?
You mean restrictions? We'll get to that in a second. And we can either do the restrictions now or later. But I'm leaving the argument being greater than 0 aside for a minute, and then we'll tackle that, okay? If log base 6 of 2x minus 11, or sorry, 2x minus 1, is log base 6 of 11, what can you tell me about 2x minus 1? Yeah.
2x minus 1 equals 11?
Has to equal 11. This is like when we were solving exponential equations, and we had an exponential equation like 2 raised to the x plus 3 equals 2 raised to the 4x minus 10. And we all of a sudden made the leap and said x plus 3 has to equal 4x minus 10. There's a reason for that, and that's that if the two powers are equal and the bases are equal, the exponents have to be equal. These two logarithms on the left are equal, and they're the same base logarithms, so the arguments must be equal. This is perhaps the simplest equation that you would see in this unit. We're simply going to solve 2x minus 1 equals 11. So I can then write 2x equals 12 rather, when I add 1 to both sides. And I divide both sides by 6. Sorry, I divide both sides by 2 to get x equals 6. Are we okay with that? Okay, now let's talk about restrictions. If I look at the argument, and I have to go back to the original equation. If I look at the argument in the original equation, the argument was 2x minus 1, and that has to be greater than 0. That's a fact. You cannot take the logarithm of 0, and you cannot take the logarithm of a negative number. So if we rearrange this to get 2x is greater than 1, and then to get x is greater than 1/2, what does that mean? Well, we should know what that means. I shouldn't need to draw a number line for something with a single inequality like that, but I'm going to anyway. What this means is that if this is 1/2 on an x number line, x must be greater than that number. It can't be equal to that number, and it can't be less than that number. It has to be greater than 1/2. So there are two ways to check the validity of our answer. One, and this is the best method. The best method to check whether this is true or not is to look at your solution that you got and compare it to the restriction. And if your solution lies in the allowable domain of x's, it's a valid solution. Okay? And I think this is the best way to go. So what we can do here is indicate that that's correct. And on a written response, of course, you would say, since it's in the domain of the allowable numbers. What some people do, and I don't think this is as good, is they will simply take that number 6. They won't even look at any of this that I've got in red. They will take that number 6 and they will put it into the equation, and they will end up with 2 times 6 minus 1. 2 times 6 is 12. 12 minus 1 is 1. Or 12 minus 1 rather is 11. And they'll have log base 6 of 11 equals log base 6 of 11, and they will check it. I don't think that's good enough, or as good as finding the restriction. Very often on a diploma exam or on my exams, one of the parts of a written response will be, what are the restrictions on x? Okay. So when we take a look at B now, let's do the restrictions to begin with. I see an argument of x there. So my restriction in this equation would simply be x is greater than 0. I think on a written response, it's a good idea to explain why. By just putting a statement that says, you cannot take the logarithm of a negative, and you cannot take the logarithm of 0. Okay, so that's our restriction. We'll come back to that. This is going to become log base 7 of 4x equals log base 7 of 12, because the sum of logarithms is the logarithm of a product. And now I hope you can see, everybody, that both of these A and B questions fall into the same category. You end up with both of these having this situation. You end up having one logarithm equals an identical based logarithm, and that means the two arguments are equal. So in this particular general statement I've got here, you would put triangle equals quadrilateral. Just like over here, we drop the log base 6s. By the way, we're not dividing by log base 6. It doesn't work that way. You can't divide by an operation. You can't divide by a square root. You can't divide by plus. You can't divide by log base 6. So what we end up with here, is very basic. We end up with 4x equals 12. I don't think I need this. You end up with 4x equals 12. Divide both sides by 4 and get x equals 3. And then you take a look at what we said about the restriction, which is at the top of the screen. X must be greater than 0. Is 3 greater than 0? Yes? Okay, well, what that tells us then is that this is a valid solution. Again, on a written response, you would explain that it's in the domain. Any questions with B? Right. Log base 2 of x plus 3 quantity squared is equal to 4. Let me rewrite this to indicate to you that this means log base 2 of x plus 3 quantity squared. It's implied. The squared doesn't apply to the logarithm. It applies to the argument of the logarithm. If it was applied to the logarithm, then you would see this. Okay? I've argued for many years, but who am I to make decisions, that we should treat logarithms like we do trig. And if we mean the square of the logarithm, we should write log squared. Nobody's listening to me. Okay? All right. This question is different than A and B. In A and B, you have a logarithm equals a logarithm. Here, what you have is a logarithm equals a non-logarithm. But we can write that in exponential form. We can say that this base of 2 raised to this exponent of 4 is equal to x plus 3 quantity squared. And now we're in a Math 20 realm, because x plus 3 quantity squared is quadratic. 2 to the 4 is 16. X plus 3 squared is x squared. X plus 3 quantity squared is x squared plus 3x plus 3x plus 9, because x plus 3 squared is that. So we zero this equation. This is definitely factorable. Two numbers that multiply to give negative 7 and add to give positive 6 are positive 7 and negative 1. Which means, by my reckoning, x is equal to negative 7 and x is equal to positive 1. Now, so any questions about the algebra there? When the argument is quadratic, which it is in this original equation, if we go back and we take a look at the original equation has an argument that is quadratic. This is the argument in the original equation. This is the original equation right here. I've just rewritten it with an extra set of brackets. Okay? I always struggle with this because there's an issue here with quadratics and inequalities. Technically speaking, you should algebraically know how to solve a quadratic inequality because it's taught to you in Math 20. That being said, I don't think anybody really remembers how to do it. Calculus students you might construct a chart where you have the zeros of x plus 3 and you do a chart where you find out where it's positive and where it's negative. But we're not going to get into that. So what I would say to you is I don't think on a diploma exam, on a written response, you would ever have a situation where what we did here to find the inequality in B, what we did here to find the inequality in A, where is it? That's fair game on a diploma exam for written response. For this question, all you need to do is say to yourself, All you need to do is say to yourself, will my solution of -7 result in a negative argument or a zero argument? And if it results in a zero argument or a negative argument, you throw it out. Will -7 result in an argument that's negative or zero? No, it won't, because the argument is something squared. It doesn't matter what you put in for x in this highlighted thing. You're going to add 3 to it, but then you're going to square it. There is only one non-permissible value here, and it's -3. Because -3 plus 3 is 0, 0 squared is 0, and that's not allowed. So both of these are valid. Again, I kind of danced around that issue, but I want to make it very clear here, try to be more succinct. If your argument is quadratic, there's no easy way to determine the domain of allowable values. You simply need to take your answers and put them in and see if they work. Okay. Let's take a look at the next question. Well, the A and B had logarithm equals logarithm. C had logarithm equals non-logarithm, and we put it in exponential form. We're going to turn this into a logarithm equals a non-logarithm. I am going to subtract log of x plus 1 from both sides. So I have log of 8x plus 4 minus log of x plus 1 equals 1. By the way, we can do our non-permissible values here right now. 8x plus 4 must be greater than 0. So we're going to solve that. We're going to subtract 4 from both sides and divide by 8. Correct? Correct? X is greater than -1/2, but we also have to do that. We also have to do that with the x plus 1, which means x is greater than -1. Wait a minute. What does that mean? How do we wrap our heads around two restrictions or two sets of restrictions? One of these is going to be consumed by the other. If I were to take a look here on a number line, and I like number lines for this kind of thing. I think it's very helpful. On a number line, here's -1, here's -1/2. On the one hand, we're saying that x has to be greater than -1/2, and on the other hand, we're saying x has to be greater than -1. Well, we can't write x is greater than -1 because that would include numbers that are not greater than -1/2. We're looking here at where these two overlap. So this is going to be the restriction. Just because a number is bigger than -1 doesn't mean it will be bigger than -1/2 as well. So now we can solve this. We're going to solve it by putting these two logarithms together and writing log of 8x plus 4 over x plus 1 is equal to 1. Now what? I'm using the quotient rule or the difference of logarithms rule. But what do I do now? Will, do you know?
You say 8x plus 4 over x plus 1 equals 0?
No. You're on the right track. What's not written in this logarithm? What's hidden The hint I will give you is where we are at right now, everybody, is exactly in the same place that we were at here. So Will, you want to amend what you're going to do here? No? Yeah. Right. There's a base here of 10. So we can write that logarithmic equation in exponential form and say 10 to the 1, which is 10. And I know why you would think 0, because exponents of 0 give you 1. But the 1 is the exponent. So now we have 8x plus 4 over x plus 1 equals 10 raised to the 1, which is 10. We can multiply both sides of that equation by x plus 1 to eliminate the denominator, and have 8x plus 4 equals 10 times x plus 1. If you want to think about what I just did there as cross multiplication, feel free. We can expand that out and get 8x plus 4 equals 10x plus 10. And, you know, now we're in a junior high-ish kind of math problem. Subtracting 8x from both sides is 2x. Subtracting 10 from both sides is negative 6, which means I get x equals negative 3. 2x equals negative 6. I divide both sides by 2. Is negative 3 a solution? No, because it's not in the domain. And we can check something out right now before I strike them from the list. If I put negative 3 in here, if I put negative 3 in here, I get negative 3 plus 1. I get negative 2. All bets are off right now. I don't even need to check the other argument. If one of the arguments is negative, the whole equation crumbles. If I were to put negative 3 here, well, I would have 8 times negative 3 plus 4. Well, I think that's negative 20. It's going to be negative. But again, they don't have to both be negative. The bottom line is when you look at the number line here at the bottom of the allowable values, negative 3 is over here someplace. It's nowhere in that domain. What that means is these two things are never equal to each other. If you graphed y1 equals the left side and y2 equals the right, they would never intersect. All right. Do the same thing here. Move the logarithms to one side. So I have log base 2 of x minus 6 plus log base 2 of x minus 4 equals 3. I really should do the restrictions before I even move stuff around. But we can still do the restrictions here. X minus 6 must be greater than 0, which means x has to be greater than 6. I also have x minus 4 must be greater than 0, which means x has to be greater than 4. I think one of the most effective ways to communicate that the answer for the restrictions is to do a number line. And I'll tell you, I had to do a number line in my head to convince myself that that's going to be the restriction. Because when I look at a number line, and I say here's 4 and here's 6, if I'm saying x has to be greater than 4 and x has to be greater than 6 covers them both. Greater than 4 doesn't, because 5 is greater than 4, but it would still make one of the arguments negative. So the highlighted is the restriction. I put these together now as a single logarithm. The logarithm of the product. that means that x minus 6 times x minus 4 has to equal 2 cubed, the base raised to the exponent. And 2 cubed is 8. Foiling out, I get x squared minus 10x plus 24 equals 8, which means x squared minus 10x plus, is it 16? 24 minus 8 is 16? Okay. Equals 0. Are there two numbers that multiply to give 16 and add to give negative 10? Well, they would have to both be negative. They would have to both be negative. And I believe negative 8 and negative 2 do the trick. What does that tell us? It tells us that x is equal to 8 and x is equal to 2. Of course, there's some missing work there that you would show on an exam. Is x equals 8 a legitimate solution? Yes. It is. Because 8 is greater than 6. Is x equals 2? No. And I used to tell people to just put this, but it looks like an x. So I wouldn't do that. I would put no, not a solution. And again, you would explain that. Any questions with that one? All right. Okay, so just put your pencil down for a second. If we do this one the way we did the one where the argument was squared, which is how you have to do it for a squared, then you would end up having this. And you're not writing this down. Would you agree? Do you really want to do that? No. Because what you would have to do to solve this is expand this out. Figure out what 3 to the 10 is and subtract it to get a polynomial of degree 10 equal to 0, and then dive into the synthetic division factor theorem pool and splash around for a half hour. Okay? Probably sinking to the bottom anyway, okay, because it's such a high degree. So what we're going to do in this particular case is we're going to use power rule and move that 5 down in front. Then we can divide both sides by 5 and get something that's workable. Log base 3 of x squared minus 8x equals 2. Well, we can do that. Again, if it's a log equals a log, you drop the logs. If it's a log equals a non-log, you write it in exponential form. And again, we're back in Math 11 at this point in time. We can zero this quadratic equation. X squared minus 8x minus 9 equals 0 because 3 squared is 9. I guess that factors into x minus 9, x plus 1, which means x equals 9, x equals negative 1. Now, you'll notice here that I didn't talk about the restrictions. And the reason I did not talk about the restrictions in this is because the argument is at least quadratic. Right? Even after we move that 5 down, the argument is quadratic. And I told you that you're not expected to be able to find the restrictions for a quadratic argument. So what we're going to do here is put 9 in here. You're going to take 9 squared and subtract 8 times 9 and see if you get a positive number. Then you're going to do the same thing with negative 1. And by my count, when you put 9 in for x, you're going to get 9 for an argument. 9 squared minus 8 times 9 is 9. Also, by my reckoning, when you put negative 1 in for x in the argument, you're going to get, strangely enough, 9. Okay. And that makes sense because log base 3 of 9 is 2, and we bring that 5 down and divide 10 by 5, and you get 2. So they're both legitimate solutions here. Any questions with F? Ooh. Okay, things have changed all of a sudden with this question. Up until now, everybody, we have had one of these two cases. You have either had a logarithm of a thing equals a same or similar base logarithm of an apparently different looking thing, in which case you do this, right? That's one of the things we do. That was like examples, that was like examples A and B. On the other hand, though, there's a second case, case 2, where you end up with a particular base logarithm of something equals another thing without a logarithm. And what you do in that case is you write it in exponential form. Those are the two big kind of strategies you can use. But this one is different. And the reason why this one is different is because of where the squared is on that log of x, log base 2 of x. What's the difference? Let me rewrite this here. What is the difference between log base 2 of x squared and log base 2 of x squared? Well, they're clearly different. I don't have brackets around that x squared, but there should be, or there could be. What is the difference here? Well, the difference in terms of our rule for a power is I can move this 2 down in front, but I cannot move this 2 down in front. This squared on the log base 2 of x is not an exponent of the argument, so you cannot move it down, because the rule says you move it down if it's an exponent of the argument. This 2, on the other hand, I can move down in front. Now, there's a lot of 2's floating around here. The 2 that I move down in front is the exponent here on the x. And this is equal to 0. So does anybody, I'm going to give you a minute to, well, first of all, are we clear that the exponent only goes down in front if it's on the argument? That's why those brackets are really crucial on your formula sheet. Does anybody have any ideas? Miles?
2 log x divided by log x. Yeah. So you just add 2 log x.
Okay. We are not allowed to do that. And I'm going to explain why. Okay? I think this is a very valuable lesson. I know exactly what you're saying. Let's imagine that I had the following equation. Just by inspection, would you agree that 2 is a number that makes that true? 2 squared minus 2 times 2. Okay. Just by inspection, would you agree that 0 is a number that makes it true? And that makes sense. 2 solutions, it's quadratic. If you do what you want to do, and it's a common thing that sometimes happens, and you move the 2a over, and you say, I'm going to divide both sides by a, I'm left with a equals 2, but I've lost the other solution. We're not allowed to divide out variables. because variables are linked to solutions. What you would do instead here, in order to get the right solution, well, what would we do? What would you do here to get the solutions? Take A out, yeah, sure. So we take an A out and have A minus 2, and then it's pretty clear that A is equal to 0, and A minus 2 is equal to 0, and are we clear that that leads you to those two solutions? Okay. Well, let's learn from that. What do you do here? What do you do when we have what's at the top left of the screen here?
You take log 2x.
Log base 2 of x out. I factor a log base 2 of x out. And I will have a log base 2 of x minus 2. Now, before in my analogy, we would just say, oh, A is 0 and A is 2. But what we have to do here is say log base 2 of x is 0, and log base 2 of x minus 2 is 0. The second equation becomes log base 2 of x equals 2. All right. Where do we go from here? Because I want to know what x is. I don't want to know what log base 2 of x is. I need to know what x is. Yeah, Miles.
You put x equals 2 squared.
Right. I convert it to exponential form. This is going to become 2 raised to the 2 is x. This is going to become 2 raised to the 0 is x. And I do understand that some of you will think x equals 2 to the 0, and others will think 2 to the 0 is x, depending on how you convert it. But we've got our solutions. X equals 1, x equals 4. If you go back into the original equation, x is the argument. X must be greater than 0. These are both greater than 0. We've got a couple more to go. This one is very similar to the one we just did, except instead of just having two terms where you factor out a common factor, we're going to have a full-blown quadratic of ax squared plus bx plus c. Of all of, well, not all, of those two exponents you're looking at, the 2 and the 5, which is allowed to be moved in front? The 5. It's an exponent on the argument. Again, there's an implication that when you see that, it's x to the 5 is the argument. So this equation becomes log of x quantity squared minus 5 log of x minus 24. And I really hope that you see how this is the same structure as that equation. If you can solve that equation in red by factoring a squared minus 5a minus 24, there is no reason why you can't factor the equation in blue. If it were a squared, you would put an a in both of the first places. Here you put a log x. You would be looking, regardless of the equation you're solving, for numbers that multiply to give negative 24 and add to give negative 5, while 3 and 8 are off by 5. So these are the numbers. Don't forget equals 0. It's not, it's not huge, but sometimes these markers are a little uptight about that kind of thing. I know I am, actually. It should equal 0. It's an equation. If you're going to do things, let's do them right. This becomes log of x plus 3 equals 0. And I apologize for the way I just said that. It sounded like I said log of x plus 3. It's not what I meant. Log of x plus 3. The 3 is not with the x. And this is log of x equals minus 8 equals 0. We get log of x equals negative 3. We get log of x equals 8. Now what? Shannon.
You put it in exponential form.
Don't I need a base for that?
It's base 10.
Right. So, and this is a confusing thing. That's perfect. Sometimes when it's a common logarithm and the base isn't written there, it kind of puts up a wall in front of people. They don't know what to do. But it is. It's base 10. So I can put these in exponential form. This is base 10. This is base 10, which means that x is equal to 10 to the negative 3. And x is equal to 10 to the 8. I don't think there's a need to figure them out. 10 to the negative 3 is 1 over 1,000. 10 to the 8 is 100 million. Those are two numbers that are both greater than 0. And when you take a look at the original equation, as long as x is greater than 0, the arguments are greater than 0. Because, why not? 4 multiplied by the base 2 logarithm of the cosine of x equals plus 2 equals 0. Well, ultimately speaking, everybody, if you want to get x by itself, then you have to get cos x by itself, don't you? Which means all of this other stuff, the 2, the 4, the log base 2 operation, we've got to peel all those layers off so we're left with cos x equals something. We can subtract 2 from both sides and get 4 multiplied by the base 2 logarithm. This base 2 logarithm, this is an operation. I'm putting that there now because I want to talk about that later. 4 multiplied by the base 2 logarithm of the cosine of x is now equal to negative 2. Before I can unpeel that operation, I need to divide both sides by 4. So now I get log base 2 of the cosine of x is equal to negative 2 over 4, which is negative 1/2. And now I have to peel off that operation. And I don't believe I've talked to you about this before, but if it's a square root, you square both sides. If it's squared, you square root. If it's plus 5, you subtract 5. The opposite operation to base 2 logarithming is to write it in exponential form, that's all. So if we write this in exponential form, we get 2 raised to the negative 1/2 is equal to cosine of x. Well, 2 raised to the negative 1/2 is 1 over 2 raised to the half. 2 raised to the half is root 2. So we have 1 over root 2 equals cos of x. You should know that on the unit circle, this is the x coordinate on the unit circle. You should also know that on the unit circle, the x coordinate is 1 over root 2. I haven't quite figured out all these things yet, so I'll just freehand it. Is 1 over root 2, at the 45-degree increments or positions in quadrants 1 and 4. So pi over 4 is a solution. And let's just run this through our heads. If x is pi over 4, then cosine of x is 1 over root 2. And when we rearrange this for cosine of x, we had cosine of x equals 1 over root 2. So it works. The other solution, of course, from 0 to 2 pi would be 5 pi over 4. But since it didn't say anything here at all about a domain, we are going to put for a solution x is pi over 4 plus multiples of 2 pi and 5 pi over 4 plus multiples of 2 pi, where n is an element of the integer number set. I wouldn't say we're almost done the course. We're almost done the 5th unit, so we only have 2 units left, and one of them is really quite short. You're going to start to see more and more questions that incorporate other units into the current unit you're studying. And that's it. I realized I was moving a little slower today because I'm trying to get used to this, but it wasn't too slow, I'm assuming. It was not too slow. So the pace was okay? All right, good. A variety of questions for you to practice, dealing with just a smorgasbord of equations that have logarithms in them. Sometimes you can get log equals log, lop the logs off. Sometimes you get log equals non-log, write it in exponential form. Sometimes you get a quadratic or a trigonometric. You just have to be creative and just dig deep and use all of those math skills that you have available. Okay? So get to work on that, please, and I will be around to help you.